So over here, this axis is our hardness. Okay. So this axis over here is what we call depth beneath, okay, beneath the newly generated surface. Okay, and then this line I'm going to draw this over here is our bulk hardness. So whatever hardness from the supplier, for example, from the supplier. Then we have scales over here. Okay. So we have scale over here. So this is 25, 50, 150, 100. Hey, what is 100? Come on, Eugene. Okay. 75, 100. Okay. So if you have low B and N, right? Remember, we talked about the cutting edge. Remember, right? We drew a diagram at the cutting edge. We drew a diagram over here, right? Right? Last week, right? Over here, we drew a diagram over here to see what is going on, right? We drew a diagram over there. So part of it will become the chip. The other part will fracture, right? To become the workpiece. The fact that he has to be fractured means he has to experience some sort of what? Strain, plastic strain. Okay. So after machining, because of the heat, because of the B and N, okay, we will have two trends. Okay. So the first trend over here, right? So for this case, you have low B and N. Okay. But when your B and N is high, okay, you have this. Okay. So over here, this is your high B and N. Right? Why is it high? Right? So for example, if they fracture, so I'll give you an example. Why is it going to be high? So if they fracture, right down here, if this is a fracture strain, you can see the high B and N, right? The stress is what? Higher. Okay. And the hardness also be affected. Right? So now, let's see what happened now. Okay. So if we were to take a 0.05 millimeters undeformed chip thickness, okay? So so this is after our first pass, okay? So the two move, it move, okay? First pass done. We measure the hardness, okay? Then the second pass, right? The cut number 2, we decide to do, okay? So we decide to do, hey, for the second cut, okay? Now we are planning. I decide to do this height over here, okay? This height over here to be 0.05 millimeter. Okay. So the depth, I do apologize. Okay. The depth beneath the surface over here, this is in micron meter. Okay. This is. So when we take 50, okay. So the next cut, 0.05 meters is 50 microns. Okay. What you see over here, right? So when your tool, is going to like, okay, your tool is going to, so I'm going to draw your tool. Okay. This is such a, I'll move this. Okay, I'll move this over here. So this for high B and N, right? So when your tool, your cut number 2, okay, so this is cut number 2, right? So this is cut, okay, cut number 2. So what is cut number 2 going to see, right? If your B and N is low, the hardness will also be what? It has recovered to its what? Bulk hardness. Yes, right? When your B and N is high, you look at this value over here. Okay. This is the hardness increase. Right? So if we were to take what? 50 microns, we're going to be in trouble. Yes or no? We're going to hit the workpiece that is going to be harder than the bulk hardness. That's going to be a problem. Okay. So now, what is the solution? Anyone? As you can see over here, the solution is what? Cut number 2. I'm going to cut at where? Oh, this is fantastic messy. Okay, cut number 2 will be at 90 micron meter. Cut number what? When you use cut number 2, the difference in hardness is very what? There's no difference in hardness, right? So by drawing this, I could like visualize what is going on. Yes or no? Right? If you have low B and N, right, you take 0.05. If you have high B and N, you need to go more. If we were to go less, remember what I call the caveman philosophy, right? All about eating and reproduction, right? If it's a caveman mentality, we will say, hey, without knowledge, okay, without knowledge, we say, let's go smaller. Okay, we go smaller. When we go smaller, what will happen? If you have high B and N, the difference in hardness will be much what? Higher. And then when you'll see your tool breaking, okay, you'll see that it's so impossible to machine. This is the reason. This is the reason why knowledge is so critical. It makes sense, you know. If we don't go through the physics of what is going on. It makes sense. If something has high B and N, let's go easy. Let's take 0.02. Bite smaller so you won't injure yourself. If you take a bigger bite, you will die, you will injure. No, this one say bite bigger, bite more, okay? And I've used such solution in my consulting before, and it works. Okay? Tooling companies or some manufacturers, they brought their researchers, they say, no, do smaller. I just say, okay, whatever. Okay, let's do smaller. And it did not work at all. Okay, it did not work at all. And then when you go bigger, it works. They're like, interesting. Yeah, there you go. The explanation why. Okay, so I'm going to write some things. Anyone, any questions so far? Anyone? Right, so now you know.
Yep. Sorry. I have a question. I was just wondering if this is true for fully annealed metals as well, since they have no difference in like their chemistry and stuff.
Good question. Fully annealed, I have no problem, right? What is critical is the B and N relationship. Fully annealed, so I'll try to recall example. So fully annealed, we talk about TRIP 800. Okay, fully annealed, very soft, easy. But when you strain it, what happened? Right? It's sensitivity to what? Strain hardening. Okay, so this is where the problem will come. Okay, so whatever heat treatment you've been through, nice. Okay, more important is how the B and N will what? Behave. Okay, does that answer your question?
Yes, it does. Thank you.
You're most welcome. And that's a good question, by the way. Okay. Now, so I'm going to write. So with depth, further away, okay, from the newly generated surface. Okay. The hardness will recover back to its bulk hardness. Bulk or initial. Can you see you can see initial. Okay, bulk or initial. Initial hardness. Okay, so the recovery depth is dependent on B and N, right? The recovery depth is dependent on one. You can see this graph down here. It's dependent on B and N. Okay, so i.e. high B and N values. Okay, if you have high B and N values, we'll have deeper recovery depth. Okay, so when that's the case, you have to adjust your process parameter. Okay, you have to adjust your process parameter accordingly. Okay, so this is a classical example. Okay, it's interesting. When it is the opposite trend, you will have a lot of opposition. Trust me, okay? When I do my consulting or when I was working Rolls-Royce, the opposition, that the disagreement comes in very, very intense. No, this is not true. You know, because why? It's a caveman mentality, right? We all think about eating. Yes, right? It's normal, okay? Nothing wrong with that. Okay. Right. So the next thing we will look at, okay? So we are going to look at effect of the effect of strain hardening sensitivity, okay, on cutter path planning. So now I'm going to introduce you to a new process which is called milling, M-I-L-L-I-N-G. Okay, during the break you can Google it, okay, or YouTube, okay, YouTube milling process. So I'm going to draw this out. Okay, so this is our workpiece. So you realize that our workpiece is no more cylindrical. Our workpiece is rectangular. Okay, so this is our workpiece. Material. Okay, and the workpiece material can move in the Z direction. Okay, and it can move in the X direction. So I want to draw my transformation now. This is my X. This is my Z. Okay, and this will be my Y. Okay, so the workpiece is able to move in the X and Y direction. Okay, then we have a tool. Okay, now the tool is rotating. Okay, so this is our neutral axis. Okay, so this is our tool holder. Right, the tool will rotate. Okay, rotate. Okay, the tool will rotate, and then we will attach. This is a schematics. Okay, this we will attach. This is our cutting tool. Okay, come on, cutting tool, or we call it the insert. Okay, and this thing can move in the Y direction. Okay, so you can move the Y, the table will the workpiece. So this is one of the configuration. So to give you perspective, okay, give you perspective, the X and Z will be moving at, in terms of velocity, is about 5 meters per minute. Okay, so it is pretty slow. Okay, so imagine that 5 meters. Okay, so my table over here is about 1.5 meters. So you walk, okay, 1.5 meter, you walk Okay, so imagine covering from here, you can cover the length of my table, 3 times the length of my table, take 1 minute. It takes forever. The rotation over here, right? That you can see over here, the linear velocity is between 200 meters per minute